relaxation oscillator, that is without giving any input. So this is UJT is going to generate oscillations or the pulses. So that is going to be relaxation oscillator, and we have seen the frequency of that. So we will see some problems on that. So first problem, if RE is equal to 1 kilo ohms and IV, that is a value current, so it's 5 milliampere, determine the value of VEE, so which will cause us UJT to turn off. Okay, so they have given RE and IV, that is a value current, and we have to determine the VEE, so that causes to turn off the UJT. So V is equal to VBB, that is a emitter voltage is equal to, that is a value voltage, it is going to be a 2 volts they are taken, that is from the characteristics they have taken, and IE is equal to IV, that is a 5 milliamperes they have taken. Okay, so then applying a KVL, so VE is equal to IE RE, that is in the equivalent circuit. If you have seen the equivalent circuit, so in the equivalent circuit, so we will be, that is we will be having, that is it is like this, and that is B to B1. So this is emitter, and we will be having RE here. So and we will be having VE here, and this will be VE. Okay, this is grounded. So applying input part of the equivalent circuit, it is going to be VEE is equal to IERE plus VE is equal to 0. Okay, so you check the input circuit, and so applying a KVL for the input part, VE is equal to IERE plus VE. So that is IE is given, so that is IE is equal to 5 milliamperes into VE is 2, so that becomes, okay, 2 into 5 plus VE is 2 volts, that is 5 milliampere, and RE is 1 kilo ohm. 5 plus 2, it is going to be a 7 volts. Okay, so VE, so that is going to turn off that is UJT. So next, the second problem. So design a UJT relaxation oscillator. So using UJT, they have given a UJT number for triggering an SCR. The UJT has the following characteristics. We have to design UJT relaxation oscillator, so that is going to trigger SCR. So they have given intrinsic standoff ratio 0.7. So IP, the peak current is given, and value voltage is 2 volts, and value current is 6 milliamperes, and VBB is 20 volts, RBB is 7 kilo ohms, and I is 0, that is a 2 milliamperes. So determine the limits of for the output frequency of the oscillator. So they are asking. So we have to design UJT, as well as also we have to determine the frequency of the oscillator. Okay, so design oscillator means the relaxation oscillator consisting of, that is resistances, capacitances, R1, R2. So that we need to calculate it. Okay, so R max we calculating, that is R max is calculating, this is the 20 is what, that is VBB. So that is V by I, that is there we are using, that is the V by I, that is R is equal to V by I, that is the Ohm's law we are using. So that is VBB into, that is I'm calculating R maximum at the peak value. So the response is going to be how the characteristics we have seen like this. So it is going to be, the maximum is going to be I peak, and this is going to be IV. Okay, V peak and VV. So this is where the R is going to be maximum. So here as voltage decreases, the current increases, voltage decreases, the resistance is also decreases, and at the peak value, the peak values, we are getting the R max. At the value point, we will be getting the R minimum. So then R max is equal to VBB into, so 1 minus eta, that is 0.7. So divided by, that is a 50 microamperes IP, that is R max, that is the maximum resistance I'm calculating at the peak values. Okay, VBB into 1 minus, that is intrinsic standoff ratio, divided by, that is a 50 microamperes, that is IP is given. So we are going to get 120 kilo ohms, and R minimum we are going to calculate at the value points. It is VBB minus VV, it is given 2 volts here. Okay, it is given 2 volts, and so they have given, that is VVB and IV, value voltage and value current. The value voltage is 2 volts, value current is 6 milliamperes. So VBB minus VVB, so divided by IV, so we are going to get R minimum 3 kilo ohms. and the approximate value of R2 is going to be given by a formula. R2 is equal to 10 to the 4 of 4 divided by the intrinsic standoff ratio eta into VBB. So then we will be finding R2 value. So next, R1 is going to be VG minimum divided by IEO. So that is VG minimum is the minimum gate voltage required to trigger the SCR. This is almost equal to 0.2 volts. So then that is IEO, that is reverse voltage is given. So then R1 is equal to, so 0.2 divided by 2 milliamperes. So it is going to be 100 ohms. Okay. So that is we have calculated R1, R2. That is a maximum the variation of the resistance, that is R is going to vary from maximum value to the minimum value. So that is in UJT relaxation oscillator circuit. So according to that, I'm going to get a, that is the pulses, charging and discharging of the capacitor. So next, so now we have to, that is a find out frequency, that is a T max is equal to, that is T is equal to what, RC into log of 1 divided by 1 minus eta, that is intrinsic standoff ratio. So according to the resistances, we calculated the maximum value and minimum values. Here we are going to calculate T max and T minimum. According to that, we will be having, that is F minimum and F max. So T is equal to, so this is the formula what we are going to calculate time period T is equal to RC log of 1 divided by 1 minus theta. So then, so substituting R, that is R maximum, C is 0.1 microfarad, and so 1 divided by 1 minus 0.7. So log of that, so we are going to get, that is a T max is 14.44 milliseconds and T minimum is 0.36 milliseconds using the R minimum value. So then, so T is equal to 1 by F or F is equal to 1 by T. So we are going to get a reciprocal of our time and frequency, and we can calculate F minimum. So F minimum is equal to, that is 1 by T max, and F maximum is equal to 1 divided by T minimum. So we got, that is the frequencies 70.72 hertz and the 2.78 kilohertz, that is a relaxation oscillator frequency. Okay, so this is the way they are going to ask problems. Okay, so next, so they ask the problems, that is to derive the expression, so that is a periodic time or frequency. Also they can ask frequency is equal to F is equal to 1 by T. So that is derivation of this expression, periodic time. Okay, T is equal to RC log of, this is 1 divided by 1 minus eta. So UJT relaxation oscillator derivation. So then, so here applying a, that is we have a that is a UJT circuit. So now applying, that is voltage across the capacitor is going to given by Vp is equal to VBB 1 minus e to the 4 of minus T divided by RC, that is the transient analysis we will do. So then Vp is equal to, we have another expression, that is the discharging when the capacitor is discharged through R1. So Vp is equal to, so intrinsic standoff ratio eta into VBB plus VD. So that is not V0, that is VD. So we got two expressions for Vp, while that is voltage across the capacitor and discharging of the capacitor. So equating the two equations, okay, we got two equations. This is for voltage across the capacitor and this is the capacitor when it is going to be discharges. So we have two equations for Vp and we can equate those two equations. So equating those two equations, we will be getting this expression. So that is intrinsic standoff ratio into VBB plus VD is equal to VBB 1 minus e to the 4 of minus T divided by RC. Okay, so here if I take this VD, which is going to be a small and we are going to neglect. So if we are going to neglect VD, VBB will be get cancelled. Okay, so then we will be having, if I take this minus that is eta that side or minus this side, it is going to become c to the 4 of minus T divided by RC is equal to 1 minus eta. So then e to the 4 of T divided by RC, this is equal to minus I removed. So then this becomes, okay, so e to the 4 of T by RC is equal to 1 divided by 1 minus intrinsic standoff ratio. So then this becomes, that is 1 by RC log of 1 divided by 1 minus eta. So then T is equal to RC into log of 1 divided by 1 minus theta. So when t is equal to t, if I am taken, so this is t is equal to rc into log of 1 divided by 1 minus theta. So that is frequency, that is equal to 1 by t, and we are going to get that is frequency expression f is equal to 1 divided by rc log of 1 divided by 1 minus theta. Okay, so this is the way we are going to derive expression for that is the time period of the that is relaxation oscillator, that is UJT is going to work as an that is relaxation oscillator. So this kind of problems they are going to ask, so you need to able to, that is a previous problem what we discussed. So designing of UJT oscillator for triggering SCR, so they can change the specification and they can ask to calculate UJT as a relaxation oscillator, and also ask to calculate, so that is frequency of the oscillator. So this is all about that is a module 1. So in the module 1 what we discussed, that is the introduction, that is a power electronics, power electronic system, so history, so some converters, applications, so we have seen. So next we have in detail discussed that is a one of the thyristor, that is a silicon control device, its principal operation, that is a VI characteristics, gate characteristics, turn on methods, turn off mechanism, turn off methods, okay, and the gate triggering methods also we have discussed. So next we will move on to this second module. In the second module we are going to discuss that is rectifiers, that is a phase control rectifiers, as well as choppers. Okay, so first I will take that is a rectifiers, so controlled rectifiers, that is AC to DC converters. So in that we are going to discuss that is introduction part. So next is the control techniques, what are the different control techniques, and a single phase half wave controlled rectifier, that is a, so in this that is a, it is a single phase or a three phase, but we are going to discuss that is a single phase. So single phase half wave, so with a resistive load as well as inductive load, and a full wave rectifier, so with a resistive load as well as a inductive load. So in a full wave rectifier we will be having a center tap as well as a, that is a bridge. So for your syllabus we have only center tap, we don't have a bridge. So coming to the, so that is introduction, the rectification. So we have seen that is a rectifier using a normal diode. So rectifier using normal diode, those we are going to call as uncontrolled rectifiers, that is the diodes will don't have any control, just to give a, that is a positive to the anode of the diode, that will be turned on. Okay, rectification is a process of converting an alternating current or voltage into a direct current or voltage. So rectifier means AC to DC conversion. So that is AC to DC conversion. This conversion we are going to achieve, this conversion we are going to achieve by using a variety of the circuits, so based on and using of some switching devices. Switching devices means the diode is also work as a switch, transistor works as a switch, MOSFET works as a switch, and thyristor is also works as a switches. So that is most commonly used switching devices are going to be diodes, thyristors, power transistor, that is a power transistor, and power MOSFETs. So these rectified circuits classified into, so these rectified, already I told that is a, the phase control converters are going to be a two types. It may be a single phase converter or a three phase converters. So but we are going to you discuss that is only single phase converters. We are not going to discuss that is the three phase converters. So again they are going to subdivide as a semi converter, full converter, or dual converter. Before that, so that is the, we have a, that is a three types, that is uncontrolled rectifier, fully controlled rectifier, as well as off controlled rectifiers. So what are these uncontrolled, fully controlled, and off controlled rectifiers? Uncontrolled rectifier uses only diodes. Okay, so uncontrolled rectifier means for the rectification process it will use only diode, that is AC to DC conversion, and DC output voltage is fixed in amplitude. Okay, so by the amplitude of the AC supply. And the fully controlled rectifiers uses thyristors. So we know this thyristor is going to be, that is in a controlled manner, so they are going to do the conversion of AC to DC. Okay, so fully controlled rectifiers uses thyristors as a rectifying so elements, and DC output voltage is a function of the amplitude of the AC supply voltage and the point and wave which the thyristors are going to be triggers. So that is, so thyristors may be forward bias, but it is going to be in a off state. When I'm going to give the pulses, so then thyristor is going to be turned on, so then the conversion process will take place. So these are going to be, so that is a fully controlled rectifiers, that is using of thyristors. So next, off controlled rectifiers. So off controlled rectifiers, they are going to so contain the mixtures of diodes and thyristors. Okay, so here that is a more limited control over the DC output voltage. So we have a three types of rectifiers, that is uncontrolled rectifiers, fully controlled rectifiers, and off controlled rectifiers. Uncontrolled rectifier uses only diodes, and fully controlled uses thyristors, only thyristors, and off controlled rectifiers uses the mixtures of diodes as well as the thyristors. Okay, so this off controlled and that is a uncontrolled rectifiers, so they are going to, that is a flow, that is the flow of power, it permits the flow of power from AC system to the DC systems, and these are we are going to call as a unidirectional, that is a unidirectional converters, that is a uncontrolled rectifiers and off controlled rectifiers, they permit the flow of power from one way, that is AC system to the DC systems. We are going to refer as, or they are going to called as unidirectional converters. So whereas the fully converter or fully controlled rectifiers, so they are going to use a bidirectional from AC system to the DC system and back to the DC system to the AC systems. So this we will discuss in the coming classes, how these fully controlled rectifiers, how they are going to be, so that is bidirectional converters. So these rectifiers also referred as, or they are going to describe, so that is depending upon the, so this phase pulse numbers. Okay, so that is rectifiers, they are going to be described by a pulse numbers. So that means if pulse number, it is directly related to the repetition period of the DC voltage. For example, the 6 pulse converter operating from a 50 hertz, that is a 6 pulse converter. So 6 pulse converter operating at a 50 hertz. Okay, so it is going to the 6 pulse converter operating at a 60 hertz. So this is going to so produce, so 6 into 5 is going to be a, so 300 hertz. It is going to, that is a 6, the multiplication of 6 and 50, it is going to be a 300 hertz, that is wave. So again, these are going to be so classified as, here I have written that is the first quadrant and second quadrant and third quadrant. So that is, we will see that is what is this first quadrant and second quadrant, the third quadrant, fourth quadrant, and that is the, we have a first quadrant plus plus and second, you know this, that is the four quadrants. So this is, you can see here, this is the first quadrant converter. So in the first quadrant converter, we have a SCR as well as a normal diode. The first quadrant are one quadrant converters. So they are going to contain controlled as well as uncontrolled rectifiers in a different circuit positions. Okay. So this is called a one quadrant. So that is a rectifier, the first quadrant it is mentioned. So they will be having, that is a, which contains the controlled as well as a uncontrolled. Uncontrolled is diode, controlled is a thyristors. So these are going to be, so this is the first quadrant or one quadrant. Okay, one quadrant converters. So next, so two quadrant converters. So two quadrant converters, it will having only, that is thyristors. Okay, two quadrants, that is, so in a thyristors we have know that, that is a power flow from AC system to the DC system and back DC system to the AC system. That is a rectifier, the first quadrant, what it is happening, so that is the power flow, it's going to permit the flow of power from AC system to the DC system. Again, it will, that is a bidirectional, what we call, that is a bidirectional converter. It also, that is a flow of power from DC system to the AC system. So this, the flow of power from DC system to the back to the AC system, so this we are going to call as the inverting mode. So that's why in the first quadrant we have mentioned it as a, that is a rectifier, and the fourth quadrant it is mentioned as a inverter. Okay, so that is, so first quadrant, that is AC to DC conversion is happening, and in the fourth quadrant it is DC to the AC, that is thyristors are able to that is permit the flow of power from AC system to the DC system as well as so vice versa, that is from DC system back to the AC system. So that's why they are going to be referred as a bidirectional converters. So next coming to the four, that is a four quadrant converters. So you can see in the four quadrant converters we have a that is a thyristors. They are going to be connected like a back to back. So with one another. So that providing a facility of for bidirectional current flow through a load. Okay, so here that is it is connecting, that is a two thyristor, they are going to be connecting like to be back to back, and they are going to give a that is a four quadrant converters. So converter 1, converter 2 and converter 3, that is all rectifier. You can see converter 1 in the first quadrant rectifier, converter 2 that is a inverter, so converter 2 again it is going to be rectifier in the third quadrant, and in the again fourth quadrant it is going to be, so that is I am having it one SCR, it is going to belong to the two quadrant. So that is flow of power from AC system to the DC system, again from DC system to the AC system. That is converting mode as well as a inverting mode is also there. So that is the flow of power from DC system to the AC system. That is the DC is converting into AC. So that we are going to call as, so that is the inverting mode. Okay, so there two SCRs means, so one SCR it is flowing flow of power that is from AC to the DC, again vice versa DC to the AC. Another SCR is also same thing, that is from AC to the DC, again from DC to the AC. That is a converter 1 and converter 2 we have seen, that is a converter 1 rectifier, converter 1 inverter, that is the first quadrant and the fourth quadrant for the converter 1, that is a rectifier 1. So next for the converter 2, that is a second quadrant as well as the third quadrant. So in this way, so that is you just remember, so that is so you need, that is the first quadrant means diodes, that is as well as the SCRs will be there. The second quadrant are two quadrants. The two quadrants means SCRs will be there. Here the SCRs are thyristors. So that is the permit the flow of power from AC system to the DC system, as well as also they will permit the flow of power from DC system to the AC system. So that's why, so that is a flow of power from DC system to the AC system we are going to call as the inverting mode. So that's why we will be getting the two quadrants for SCR. So if I use the two SCRs, so I will be getting the four quadrants. Okay, so next we will move on to that is the control techniques. So we'll be having that is the three control techniques here, that is the phase angle control. It is also called a firing angle control and extinction angle control and pulse width modulation control. First we will see that is a figure, it is going to be shows, that is we have a AC supply is given and the LS inductor is connected and we have a switch S here and we have resistor. This is off-wave controlled converter using unidirectional switch. This figure is shows that is a technique of controlled conversion from AC to DC for an off-wave rectifier circuit. It is uncontrolled and off controlled rectifiers, so they are going to permit the flow of power from AC and we are going to, that is a switch SC is turned on and it conducts the current in the direction of the arrow. So that is they are given arrow, so that is going to be when going to connect, that is switch is so turned on, that is a switch means I am going to use maybe diode or maybe there is a thyristor. So then it is going to conduct, so in the direction of the arrow it is shown, and output voltage waveform depends upon the switch control and pulse triggering switches such as, so I'm going to use an SCR, I'm going to use other devices like the gate turn off devices. Okay, so MOSFET, that is a power MOSFET, so level triggered switches, so we are going to call that is a level triggered switches, maybe power MOSFET or power BJT as well as IGBT. So next we will move on to, this is a phase angle control so technique, it is also called a firing angle. So you can see that is a circuit here, that is a supply voltage. Supply voltage is going to be, the supply voltage is given, that is AC signal, so ES is going to be a EM sin omega t. Okay, so you can see that is the load voltage, So load voltage, you can see that is the second part. And so the control voltage EC, that is the pulses what we are given. So pulses we are going to give for when I'm going to use. Pulses will be given. So when I'm going to use, the switching device is going to be SCR or GTO. Okay. So next we have given the control voltage EC. So this is for a MOSFETs, BJT as well as IGBT. So you can see where the pulse is given. So that time, so this is off wave it is taken. That is previously what we were taken. That is a off wave unidirectional when current is flowing from, that is from AC system to the DC system. That is a power flow from. Okay. So whenever I'm going to apply pulses, and this switching device is going to be turned on. So that is, so pulses we are applying when our switching device is going to be SCR or GTO. Okay. So and this, that is like a square wave, that is the entire. So you can see this is going to be your conduction part of the switching device. Okay. So if when I'm going to apply pulses, then SCR is going to be turned on and it is going to be conducting. So this is during the positive off cycle, you can see. So in the waveform, positive off cycle means it is going to be above the reference. Negative off cycle means it is going to be below the reference. So when I'm going to, during the positive off cycle, I will apply pulses here. That is when I'm going to use the switching device as SCR. So when a pulse is applied, so to the, that is a gate terminal of the SCR, and so SCR is turned on, and your, that is a load voltage. So VL is equal to V naught is equal to, that is input voltage. You can see here this is going to be the, that is what I am getting during the positive cycle. This portion of the input, that is, so this portion of the input. So this portion of the input is what we are having here. Okay. So that is, so when the I'm going to apply gate pulses, that is a gate pulses, that is the pulses to the gate terminal of the SCR. SCR is going to be turned on. So then I'm going to get, so V naught is equal to VL is equal to ES only. Okay. ES is what? Your input voltage. Okay. Next, during the negative off cycle. So during the negative off cycle, I'm applying a reverse voltage means it is going to be turned off. So we know this. So this kind of turn off is going to be called a natural commutation. It is also called a line commutation. Okay. So that is naturally it will turn off when I'm going to apply the reverse voltage. So during the negative off cycle, you can see this is output voltage is 0. During the negative off cycle, it is going to be turned off. Okay. Yes, that is SCR is turned off and current is equal to 0. V naught is equal to 0. So this when I'm going to apply the SCR. So for the other devices, so that is so this kind of signals, that is a square wave kind of a signals I'm applying. This is for the MOSFETs, IGBT as well as BJT. Okay. So here you can see for the entire cycle. So up to what time you are applying, that is for the positive off cycle. For at what time you are applying this. So this is going to be this pulse. So then it is turned on, and so when the positive off cycle, that is a positive voltage, supply of positive voltage is finished, and so this is going to be turned off. When I'm during the positive off cycle, when you are going to apply, that is a continuous signal, that is when you are using, that is a MOSFET or IGBT or BJT as a switching device, and apply the reverse voltage during the negative off cycle. So this device is going to be turned off and V naught is equal to 0. Okay. Again, when you are applying the pulses, so are a continuous signal, so then it is going to be turned on. So this they have shown here. Here they have shown this is alpha. You can see here this is alpha, and so here the delta is also shown. So this is the width of pulse they have mentioned here. Okay, delta, you can see the width of the pulse, and alpha is a firing angle. So alpha is the firing angle, or it is going to be phase angle. So at what angle? So that is, so it is going to be turned on. So that is at what turned on. So that is going to be, that is a phase angle. So maybe here because I'm applying, that is positive voltage, the alpha is going to vary from 0 to 90 degree, because during the positive of cycle, so at which angle, so I'm for which alpha, that is, I can here you can see it is nearly, so this is going to be, the middle is going to be a 180 pi by 2, and it is less than pi by 2, alpha is less than pi by 2. I can make alpha greater than pi by 2 also. So then, sorry, this here alpha is going to vary from 0 to 180 degree. This is up to this you can get. So that is, so in a controlled manner you can turn on. So this is going to be a phase angle alpha. What? So we are having, and the tilde is going to be a width of this. Okay, so depending upon this alpha, that is a firing angle, so how you are going to, in a controlled manner, that is a using this firing angle, that is a phase angle, so how I'm going to, that is, so I'm, that is, if it is alpha is equal to 0, what will happen? Alpha is going to be some 20 degree, then the I will get, so SCR will be start conducting from that. Alpha is equal to 0, what will happen? Alpha is equal to 0 means, so I will get the waveform like this, right? So I will get the waveform like this. That is alpha is equal to 0. I am not playing. So then pulses is going to be, I will get like this only. That is a positive off cycle. Okay, so then alpha is going to be 5 degrees, or alpha maybe it is going to be a, so 10 degrees or 15 degrees. So here alpha can vary from 0 to 180 degree, because I'm applying a, that is a sine wave. So up to this you can get. Okay, so if it is going to be 180 degree means what will happen, alpha is going to be a 0 degree means what will happen. So in the next coming classes we will see, that is how the waveform is going to differ for different firing angles, that is 45 degree what will happen. So next for 0 degree what will happen, 90 degree what will happen. So that is, you have to observe the differences in the output waveforms. So next class I will continue with this. If you have any doubt you can ask. So we have less than 1 minute. So I think some of you are asking that the syllabus is going to be more. No, syllabus is not 4. I'm repeating again. Syllabus for the next week test. So what they are going to do with the video. Okay. So that is bridges full, AC bridges and DC bridges, as well as also that is a module 5 complete syllabus of module 5. Okay, transducers, that is a instrumentation amplifier, as well as PLCs. Module 5 full, as well as